Hello, everybody. So, on Thursday, I started discussing a couple of things, mainly neural control of respiration, which is usually where my brain goes, but we have to talk about a lot before we get to there. So, today I'm going to cover chapter 17 in your book, and that's the mechanics of breathing. And there's a lot of information in that chapter, and I'll cover most of it here, but as you'll see, you can kind of distill that down to a few, I hesitate to say simple concepts, but a few pretty straightforward concepts. The respiratory system, as I mentioned the other day, is composed of the lungs and all of the tubing that goes into the lungs, and it's primarily for oxygen carbon dioxide exchange. We bring oxygen into our body and drop it off at the erythrocytes, like we talked about with the circulatory system. And then our blood drops off carbon dioxide that we exhale, and that carbon dioxide is generated by breaking down or oxidizing the fuels that we put into our body. So what we eat comes out as carbon dioxide. And then when we breathe in oxygen, we breathe it back out in a reduced form because it is the ultimate electron acceptor, the ultimate oxidizer in our body. So we breathe out the oxygen as water vapor. Another thing that the respiratory system does, and this is kind of a secondary function, is it regulates pH. And it does this because carbon dioxide turns into H2CO3 or HCO3, and these are acids. I'm being nitpicky about my drawing here. So they're acids. And they get into the blood and they can regulate blood pH. So if our blood gets too acidic, one thing that happens is we start to hyperventilate or increase our respiratory rate. Another secondary function is vocalization. So we vocalize using our respiratory system, and this is because we have something called a larynx. And then finally, water loss. And you don't think about this as a function, but we can expel some water through our respiratory system if we want to, and we also do so inadvertently. A major source of water loss is respiration. And then heat loss. It's just a little delta if you're chemistry inclined. You're used to that. But heat loss happens by respiration, and we really see this in dogs and cats. Birds will hyperventilate when they're overheated. But to go to a number of figures that I downloaded from this chapter, we have this here which shows really the anatomy. I'm not going to spend too much time on it, but you have the larynx, which is the start of our lower respiratory system. The pharynx is shared between the digestive system and the respiratory system. You have a nasopharynx, which includes your nasals or your nose, your oropharynx, which is your mouth, then your laryngopharynx, which is just superior to the larynx. Once you enter the larynx, the digestive system kind of takes a right turn to go dorsal to the larynx, to the esophagus. We don't talk about that in physiology. I wish we had more time in this semester. We're really starved for time. But you go into the larynx, then the trachea. The trachea is the first tube that is solely dedicated to getting air into and out of the lungs. The larynx is, but we don't really consider it a tube. It's a series of cartilages with some smooth muscle in there, but also some skeletal muscle to help us regulate our voice. So we can talk really high, really low. That's because we can pull on those tracheal cartilages and modulate our voice. Then these split into primary bronchioles, secondary bronchioles. Then as you get down into the lungs, they divide and divide and divide into smaller and smaller bronchial tubes, which increases the total cross-sectional surface area. Just like in the blood vessels when we talked about that. You have much smaller tubes, but many, many more smaller tubes. And then it finally ends down in the alveoli, which is a blind sac, and you have a blow-up of one of these alveoli right here. It's a blind sac in mammals where respiratory exchange occurs. Now there are two very important types of cells in the alveoli, and they're named very logically: alveolar type 1 cells and alveolar type 2 cells. The type 1 cells, these are for respiratory exchange. Those are the alveolar type 1 cells. The type 2 cells function in respiratory exchange. I'll draw it down here because I'm running out of room. The type 2 cells secrete not mucus, but a surfactant. And surfactant is a fancy word for soap. It's amphipathic, which we covered this word when we first talked about phospholipids. Amphipathic means that it has a hydrophobic and a hydrophilic end. And we'll talk about why that's important in a few minutes. A third cell type that you have in your alveoli are alveolar macrophages. And as the name would suggest, they eat up things like particles that make it into your alveoli. Bacteria, viruses, any nasty stuff that might make it down there. These macrophages are there to eat up and then take off to your immune system. But I want to cover a couple of things. Before I get too micro, I want to talk about a couple of things in the trachea and in the bronchial tubes as well. If you remember, we talked about these guys here, the mucociliary escalator. You have your goblet cells, which are mucus secreting cells. Then you have your pseudostratified, just meaning that all of the cells touch the basement membrane, but some of them are taller than others. Pseudostratified, columnar. You can see that they're columns. This is to differentiate them from cuboidal or squamous. Ciliated. You can see they have cilia all out here. Epithelial tissue. So pseudostratified, columnar, ciliated epithelial tissue line the trachea and the bronchioles. And what they're doing is they're beating stuff up toward the larynx. And as they get to the larynx, they take a turn, go ventrally down the esophagus. And what they're carrying is all these little particles here, a lot of bacteria, viruses, dust particles, skin particles, bugs that make it into your trachea. Anything that makes it down into the trachea is going to get pumped back up the mucociliary escalator to the larynx and down the esophagus. Now, an important component of the mucociliary escalator is these channels called the CFTR channels. They allow chloride to enter the lumen of the trachea. So you're pumping chloride out of the cell. And this is done with a exchanger, the NKCC, or the sodium potassium chloride channel exchanger. You get two chlorides, a sodium and a potassium going into the cell. And the reason a sodium and a potassium go into the cell is because you need to even out this two negative charges. And then as you travel across the cell, the chloride gets pumped out into the lumen of the cell. Into the lumen of the trachea. Now, as chloride flows out, sodium is going to follow here. Sodium and chloride make salt, so water follows because this gets more and more concentrated. So this is all just law of mass action flowing. But the importance here is that salt water forms a nice slippery slick right on these cilia, allowing the mucus that's secreted by the goblet cells to flow nice and seamlessly up as these cilia beat it upward. So the watery saline layer allows mucus to flow upward. The reason it's called the CFTR, it's named after cystic fibrosis. And if there's a mutation in this channel, the CFTR channel right here, you don't pump the chloride out, you don't get the sodium to come out or the water, you don't have any salt water, and what happens is this mucus really starts to coagulate and get really thick, and it doesn't come out of the lungs, so your lungs just fill with mucus, and it's fatal. Now, if you remember, I mentioned when we talked about the heart, this is the right atrium, right ventricle, left atrium. The volume, the cardiac output of the right equals the cardiac output of the left. It just has to, because you would end up in an imbalance between your pulmonary and systemic circuits if that weren't true. The big difference is that pulmonary blood pressure is equal to about 25 during the systole. Remember, this was on the left side 120, and this is in millimeters of mercury. And 8 during diastole. So the pressure drops almost to 0. And it was 10 times that in the systemic circuit. So much, much lower blood pressure in the pulmonary. And one reason is there are so many capillaries. In the lungs. So they have a really, really, really high cross-sectional surface area altogether. They're also very short, not just the capillaries, but the pulmonary circuit altogether. And if you remember, the length of the blood vessel is one thing that can modify pressure in a system. Now that leads us to talk about some vocabulary. Our tidal volume is about half a liter, nowhere near the size of our lungs. Our lungs together, maybe 4 liters or so. And we'll see that in just a moment. But our tidal volume, when we breathe in and out, when y'all are sitting here listening to my lecture, unless you're overly excited about my lecture, as you should be, your tidal volume is about 500 milliliters, and that's the amount of air that you take in and breathe out with every breath at rest. Now, I think it should be pretty obvious that this isn't the total amount of air that you could breathe in, because at any given point, you can gasp and breathe in, right? Or say you breathed out and then you have to breathe out more. You can always breathe out just a little bit more, right? So this little bit that you can breathe in and little bit that you can breathe out are kind of logically called your inspiratory reserve and your expiratory reserve. Now, it doesn't matter how much of your expiratory reserve you breathe out, you always have a little bit of residual volume in your lungs. And it's about 1 liter. It's not really negligible. So this residual volume, you never breathe all the way out, and there's no way we can really measure it. But we know it's about 1 to 1.2 liters. If you take all of this together, which this person has pretty good sized lungs, about 5,800 milliliters are in your lungs. Now, what you breathe from a forced inspiration to a forced expiration is called your vital capacity. And this is about how much air that you're able to breathe in and out in any given breath. One term that's not so commonly used is your functional residual capacity. And it's just the amount of air that's left in your lungs during tidal volume. Now, when you breathe this entire upswing, now when you breathe in, whether it's during resting breathing, your tidal volume, or your inspiratory reserve, this is primarily controlled by your diaphragm. So your diaphragm is your primary inspiratory muscle, and we'll talk about how that happens in just a moment. Also are your scalenes, sternocleidomastoid, one of my favorite muscles. Also, all of your intercostals. You have, 4 layers of those? Muscles of your back, your iliocostalis, anything that connects to the ribs can really help with inspiration or forced expiration. So let's talk a little bit about how that is controlled. And it's controlled by modulating pressure in your thorax. And there's a scientist a while ago named Boyle, and he made up a law. So we've got Boyle's law. And what he said was basically if you have a container with a specific volume, so we'll just call this volume 1, and you change that volume to a new volume. Basically, you could think of this as if you take a balloon and it's about 1 foot in diameter, and then you squeeze it down to where it's only 1/2 foot or 6 inches in diameter. If you measured the pressure when it was that first volume, the pressure is going to be proportional to the change in volume. So what you did is, in my little example, you halved the volume. So you're going to have to double the pressure. Hopefully that makes sense. So basically, you've got this big ball, and then your pressure is 1, we'll say. Now, if you shrink it down to half that size, the pressure is going to have to double because this shrunk by half. And what that gives you is that the product of P pressure times volume, this would equal 2 times 1 equals 2, is equal to the pressure in the second condition times the volume in the second condition. And what this means, what the functionality of this is, if you increase the volume, so conversely, unlike here where we decrease the volume, if you increase the volume, So if you increase the volume by a factor of 3, if you know the pressure and you say it's 3 here, what's it going to have to be here? 2 times 3 is 6. So 6 times what is 6? We know it has to be 1. Because P1V1 always equals P2V2. We could draw this. I'm using some algebraic assumptions here. P1 times V1 equals P2 times V2. If you leave it blank in algebra, any kind of math, that means multiplication. Now, one other law that we have to talk about is another guy named Dalton. And this also has to do with pressure, but it has to do with partial pressures. And this is a very basic concept. I mentioned it the other day, but the partial pressure concept that Dalton came up with is that the partial pressure, or PP, of a gas equals the percent of that gas in a system, and system meaning just a solution like air, times the pressure in that air. So if we take air at sea level, it's 760 millimeters of mercury, and the oxygen percentage of air is about 20%. So, to figure out what the partial pressure of oxygen is, we would just say 760 times 0.2, because 20% is 0.2, right? So, this would equal, what is it, 1,420? I think so, 1,420. And then you have to put that point there. So, 142 millimeters of mercury. I think that's right. So it's about 140 millimeters of mercury for the partial pressure of oxygen. Now this is going to be very important when we talk about gas exchange at the blood at hemoglobin. We'll talk about that on Tuesday and again on Wednesday, and then we will move into the lungs a little bit on Thursday, or the kidneys a little bit on Thursday, because I want to discuss that just briefly. But so the two things that I want you to know are Boyle's law, and this is P1V1 equals P2V2, and Dalton's law, which is partial pressure of a gas equals the percent of that gas in solution times the pressure. Or we just write P because that's what we did up there. And 760 millimeters of mercury is just air pressure at sea level. Now this diagram here shows inspiration and expiration during breathing. And what we can see is, here's the tidal volume. If you remember from the graph before, tidal volume goes up. It's about 500 milliliters. Remember way up here, we showed 500 milliliters is tidal volume. So no change here, just tidal volume going up, down, up, down. And this is the data that we would have collected in lab were we in class. And it shows the tidal volume of a resting individual. Now importantly, as the diaphragm pulls down, what you're doing is you're decreasing the pressure of the thorax. And if you remember from anatomy class, all of our organs are wrapped in serous membranes. And these serous membranes are connected to the deep fascia, which is connected to our muscles, connected to the inside of our rib cage, in the case of the pleural sac, which is the serous membrane that surrounds the lungs. So when I breathe in between breaths, it's kind of forced inspiration. So my scalenes are working. Actually, my pectoralis minor is working a little bit, but primarily it's my diaphragm that's working. And what that's doing is expanding my rib cage, increasing the volume of my rib cage, and decreasing the pressure in my pleural sac. We call this the intrapleural pressure. And you can see the entire time that I'm inspiring, the pressure in the pleural sac is dropping. So the pressure in the pleural sac drops the entire time that I'm breathing in. You can see that right here. It's different in the lungs. So as this causes a vacuum in the alveoli, air starts to come in, so this vacuum dissipates because you're filling the vacuum, causing air to rush in. Now, even though you're still sucking because you still have this vacuum, the pressure starts to gain because what's happening is air is flowing into these alveoli and filling them up. Then you start to breathe out, and what happens is you start to push because your abdominal organs, your liver, your stomach, your small intestine, all push up on your diaphragm, which further increases the pressure, causing you to breathe out. Now, the whole time you're breathing out, intrapleural pressure is going up, but it only goes up to a point in the alveoli because then the air starts to go away and that pressure that's built up comes right back down to zero. Okay? And you can see here, intrapleural pressure never gets to zero. There's always a vacuum in your pleural sac. And this is really because at birth, or not really at birth, but in utero, the the thorax expands a little bit. The pleural sac is already connected to the lungs. It's connected to the ribs. And that increase in volume or size of the thorax causes the pleural sac to form a small vacuum. So at its highest pressure, it's about 3 millimeters of mercury below atmospheric pressure. Now, unfortunately, if you get a knife in your thorax and it punctures your pleural sac, what that can do is cause your lung to deflate. That's what you call a pneumothorax. And this can be a pretty big medical emergency. If you have a normal a pneumothorax, then you need to be taken to the hospital. What they'll do is they'll close this wound up, and sometimes they do need to reform the vacuum, but typically your body will work on its own to reform the vacuum, reabsorb the blood, and you're good to go. Now, if you remember, the diaphragm it's a skeletal muscle because all of us can breathe. We can control our breath. Remember, you cannot control smooth muscle. So it's a skeletal muscle, so it is innervated by a somatic motor neuron, which hits on a motor end plate, releasing acetylcholine, which causes an action potential, on and on and on, and causes flexion of the sarcomere. Now there's a virus called poliovirus that causes a disease called poliomyelitis, which causes the degeneration of somatic motor neurons. Now, and it struck kids more than adults for multiple reasons. But one of the devastating things about this disease was, and we typically think of individuals not being able to walk, that's because it degraded their somatic motor neurons, and those were the individuals that survived. But a lot of times it would degrade the phrenic nerve, which is the nerve that innervates the diaphragm. And these individuals would have to lay in basically this huge box, and just their head would stick out. And it was a pressure-controlled box that made the vacuum. And you have their head sticking out because you don't want to stick somebody into somebody's mouth into the vacuum. But it basically breathed for them. And this was a all too common sight in the 1930s and 1940s. And in the 1950s, Jonas Salk developed the vaccine for polio that worked well, and it's been eradicated from most parts of the world at this point. Now, one thing that these changes in pressure really rely on is two qualities that we covered at the very beginning of the semester, termed compliance and elastance. And we typically don't say elastance, so I'll draw what we typically say. We say elasticity. And we think of these together typically, but a compliance is the propensity of tissue, or an object, but in this case tissue, to stretch. The amount of stretch it can have. And very closely related to that is elasticity, and it's the ability of that substance to recoil. So if you have a tube like this and you stretch it out to this without it breaking, it's very compliant. So it has a high compliance. Now, if then when you let it go, it goes back to the same size, it's got a high elastance or elasticity. Now, something with high elasticity that we can think of is a rubber band. Something with a really low elasticity would be a tomato. If you take a tomato and you stretch it out, you're not going to be able to get that tomato back. Right? So that's really low elastance and not really good compliance either. But these alveoli have a wonderful compliance and a wonderful elastance. And the compliance is achieved due to connective tissue, but also when you're working on these tiny little scales, the compliance has to do with another law of Laplace. And the law of Laplace actually works against the compliance. But it's important to talk about here. So the law of Laplace states that as you work with small volumes, water is very sticky. And Laplace is turning over in his grave right now because I just uber simplified his law. But that's basically what it is, because water has these hydrogen bonds. If you're working on a very microscopic scale and water is in a chamber, it's going to really hold it together. It's going to keep it from expanding and decrease the compliance. Now, if you remember, 20 minutes ago or so, I was talking about these cells right here, the alveolar type 2 cells that secrete the amphipathic soap. It's called a surfactant in this case. That's why the type 2 cells are extremely important because what they're doing is they're secreting this surfactant into the alveoli, and that breaks the hydrogen bonds between water molecules. This goes all the way back to high school biology, where you learned about hydrogen bonds and why that causes surface tension, why that causes water adhesion and water cohesion. Water is adhering and cohering in the alveoli, especially on this microscopic scale, and you break those hydrogen bonds with a surfactant that is amphipathic, so it just disrupts the water tension, increasing the compliance of the alveoli. Now, the connective tissue is very elastic, so you have really good elastance. Now, there are a lot of lung diseases that affect the compliance and elastance of alveoli. One thing that can disrupt the compliance is asbestos poisoning, fibrosis due to asbestos or other lung disease can decrease the compliance, and this is typically called restrictive lung disease. Emphysema is actually the converse of this, and in emphysema, individuals lose the elasticity of their alveoli. So it's not that they can't stretch, but they can't really exhale. They breathe in and their their alveoli don't recoil, so the air is stuck in there. Another thing of concern for a loss of compliance is fetuses, or when they're born, so babies, who are born premature, over 15 weeks premature, which is pretty premature. Their alveolar type 2 cells are not mature enough to be creating the surfactant yet. So it can be very dangerous, and it used to be a death sentence if babies were born before 25 weeks. Now there are some intensive therapies that can start to try and fix this problem. Now, just a couple more things before we start talking about gas exchange. And this has to do with gas, but it really just has to do with the physiology of this really has to do with the physiology of the bronchioles and the pulmonary arteries. And we'll skip over to this column here because we've already talked about that column. Now, as carbon dioxide increases in tissue, in your gastrocnemius, say, it makes sense that blood vessels would dilate, right? Because more oxygen needs to be brought and blood is carrying oxygen. Now, as carbon dioxide increases in the lungs, the bronchioles are going to dilate to bring in more oxygen, right? But the pulmonary arteries constrict because there's no reason for them to flow to a space that has high carbon dioxide. Same thing with oxygen. As oxygen decreases, bronchioles are going to dilate, and pulmonary blood vessels are going to constrict because they don't want to go there. So it's the opposite in the pulmonary arteries than it is in the bronchioles and the systemic arteries, because pulmonary arteries have a different function. What they're there for is to pick up oxygen. If oxygen is low, They don't need to flow somewhere. And really, when you're sitting down, tidal volume, the majority of your pulmonary arteries are constricted down and closed. These capillaries in the pulmonary circuit are collapsible. So at the top of your lungs, they're really closed. Now, the blood vessels in the lungs have receptors for oxygen, and low oxygen in the lungs, again, constricts these blood vessels. So it's a pretty interesting physiology there. And this is one last graph that I'll show you in this lecture. And basically, it just introduces the term hyperventilation, which is breathing a lot, and hypoventilation. And it shows you the alveolar partial pressures of oxygen. And you can see the partial pressure of oxygen in the alveoli increases from hypoventilation up to normal ventilation, exceeding, and you can only get it up so high because you can't really get the air in your alveoli up above the partial pressure of the oxygen in the air. And that's about 120. It really is about 160 in the air, but because when we breathe in, we clean the air, we supersaturate it, it gets up to 100% humidity, and it gets up to the temperature of our body, which is 37 degrees Celsius or 98.6 Fahrenheit. So it sits right around 100 typically, and the maximum we can get it to is about 120 millimeters of mercury. I know when we did the calculation earlier, it was I was rounding. So the partial pressure of oxygen in the air is actually around 160 millimeters of mercury. But the highest we can get it in our alveoli is 120, and that's only when we're really hyperventilating. At the same time, carbon dioxide is going to get low in our alveoli. Okay, so we'll talk about all of that gas exchange in the next lecture that I put out, maybe tomorrow, but on Tuesday I want to really just talk about this lecture. Okay, see y'all Tuesday.